Hello and welcome to another episode of Classes with Atish. In today's episode, we will cover the concept of center of mass. Center of mass is a point where we can assume the mass of a distributed system or a mass of a continuous system is concentrated. So, if the entire mass of a distributed system or a continuous big system was to be concentrated at one point, then that point will be the center of mass. Different parts of a body might be having a very complicated motion, but the motion of the center of mass is simpler and easy to study. For example, if you have a ball and you put some rotation on the ball and throw it, let's say at an angle, okay. So let's say this is your coordinate system and you have a ball and you put some rotation on it, okay, and you threw it at an angle up, okay. So what will happen? The ball, let's say this is one point on the ball, that point is rotating, okay. That particular point has a very complicated trajectory, but the center of mass of the ball, which is at the geometric center, that exactly follows the path of a parabola, okay. Similarly, let's say we have a wheel, okay, and it is moving forward, but it is also rotating. So it's not slipping, it is rotating. Different points on the wheel have different motions at any time. For example, this point actually moves with twice the velocity that of the center of mass of the body. This point is actually stationary all the time, okay. So to study different points motion, it becomes very complicated, but if you approximate this into the motion of one single point, which is the center of mass of this wheel, then studying that motion is pretty simple. Same way, studying the center of mass of this ball, the motion of the center of mass is pretty simple. So that is why we study center of mass, okay. Now if we have a system of particles, let's say of mass m1 at some radius or some position r1, we have another mass m2 at some other position r2, okay. Like that we have a system of n bodies where the nth body is mass mn at a position rn, okay, from a given origin. So what would be the center of mass of this distributed system which has n particles in it, okay? Let's find that out. So the center of mass, let's denote by RCM, the position vector of the center of mass. Let's say the center of mass is here. This is the position vector of the center of mass, will be equal to m1 times r1, let's denote this as vectors, plus m2 times r2. Like that, if we add up all the mass times position vectors of each of those point masses, and then we divide by the total mass. So that gives me the position vector of the center of mass of a distributed system, okay, or a system of n particles. Alternatively, if we represent the position of each particle in that distributed mass as xn, yn, zn, or the ith particle as mi, and at a position vector of xi, yi, zi, then we can write the x coordinate of the center of mass will be m1 x1, or actually we can get rid of the vector notation here. So m1 x1 plus m2 x2, like that all the way to mn xn, divided by m1 plus m2 plus mn. Okay. Similarly, we can write ycm and zcm. Okay. So that is how we define center of mass. Okay. Now, if I denote the total mass of the system by a capital M, so basically m1 plus m2 all the way to mn is capital M, then what the center of mass really means is, for the entire system, the full mass capital M is as if it is at RCM position vector. Okay. So we can actually write these simpler in a different notation, xcm as 1 by m sigma summation over all particles mi xi. Similarly, ycm as 1 by m sigma summation over all particles mi yi, and zcm as sigma summation over all I mi zi. Okay. Okay. Now let's solve a few problems and apply what we just learned. Let's say we have, so this is the x coordinate, this is the y coordinate. Let's say we have a mass m at 0, 1. We have another mass 2m at 1, 1. We have another mass 3m at 1, 0, and a mass 4m at 0, 0. Okay. Question is, find the center of mass of this distributed system. Okay. Now, how we will approach this is, when we have to find center of mass, we have to find center of mass with respect to a origin position. So let's choose this as our origin, and we want to find out in this coordinate system where our center of mass lies. So we are only dealing with x and y coordinates, so we can forget about the z coordinate for now. So xcm, the formula is what? m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 divided by m1 plus m2 plus m3 plus m4. Okay. Now let's say 4m is our m1, m2, m3, m4. Okay. So m1 x1, position of x1 with respect to origin is 0. So this is 0. m2 x2, m2 is 3m. What is the x coordinate is 1, so times 1. Plus m3 is 2m. What is the x coordinate is 1. And m4 is m. What is the x coordinate is 0, so it's 0. And the total mass is 4, 5, 6, 7, 8, 9, 10, 10m. So xcm evaluates to 5m by 10m or 1 by 2. Okay. So we now know that the center of mass is somewhere on this line, where this is half comma 0, this point. Okay. Now let's find YCM. Now YCM similarly we will start with here 4m times 0 is 0, 3m times what is the y coordinate is still 0. This one 2m, y coordinate is 1, plus m, y coordinate is 1, divided by total mass 10m. So it's 3m by 10m. So 3 by 10. Okay. So somewhere here, which is 0, 3 by 10. So our center of mass is here. Okay. Now let's look at another question. We have another arrangement where we have 3 masses. Okay. This is m, this is m, this is 2m, and they are at the vertices of a equilateral triangle. Okay. So maybe this is 1, 0. This point is -1, 0. This is 0, √3. Okay. So question is find the position of center of mass of these 3 masses. Okay. So again similarly we can choose this as our origin, and with respect to the origin we will find out the center of mass. So we can write xcm. Let's take this one first, m times 1 plus next this one 2m times 0, because this x coordinate is 0, plus m times -1 divided by 2m plus 2m, 4m. Okay. So this comes to be 1m minus m by 4m, so 0. So we know the center of mass is on the y coordinate or the y axis, okay, which is pretty obvious because it's equal masses on the other side, 2m is on the y axis, so it is, you can think about this, that this will be on the y axis. Okay. Now let's find out YCM. So YCM, this term is m times 0, this is 2m times √3, again this is m times 0 divided by 4m total mass. So this is 2 and 2 gets cancelled, so √3 by 2. So somewhere here. So x coordinate will be 0 and y coordinate will be √3 by 2. Okay. Next up, let's look at a three-dimensional figure now. Let's say this is my x, y, z coordinates, x, y, z. Okay. And we have a cube of side A. Okay. So then each of these coordinates will be, oh, this is x, right? So A, 0, 0. This will be 0, A, 0. And this will be 0, 0, A. This coordinate will be, we are moving A in the x direction, A in the y direction, and nothing in the z direction. This coordinate will be, we are moving A in the y direction, A in the z direction, and nothing in the x direction. This is, we are moving A in the x direction, nothing in the y direction, and A in the z direction. And this one, we are moving A in all three directions. Okay. Now let's suppose on each of these vertices, there is a mass m. Okay, equal mass m. Okay, I'm not going to write everything, but let's suppose each of these vertices have a mass m. Let me just write it down. Okay, find the center of mass of this system. Now, yes, you can start to do all those calculations, but visually you can also get a feel of it. Since it's all equal masses, it must be, so x cm, y cm, and z cm should be equidistant from all the edges. So a by 2, a by 2, a by 2. Okay. So it will be somewhere, so in the x direction a by 2, in the y direction a by 2, and in the z direction a by 2. So somewhere here inside the cube. Okay. For any closed body, can the center of mass ever be outside of the body? It's not possible. It will always be inside of the body. Okay, so something to think about. Okay, let us take another example. Maybe I will write it down somewhere here. So let's say we have two plates or a square. Let's say we have a square, okay, where each of these vertices have mass m. Okay, and then there is another square, each of these vertices have mass 2m. Okay, and the distance between these squares is maybe d, okay, from the center point to center point, or from any corresponding vertices, the distance is d. Find the center of mass of this system. Okay, again, you could choose a coordinate system, maybe have the origin here and then do all the math, but sometimes these problems you can also visually figure out the center of mass. For example, if you just look at this system here of 4 m's, obviously the center of mass will be right at the geometric center here, and the entire 4m mass will be concentrated in this point. Similarly, for this square, the entire 8m mass will be concentrated at the center of the square. So the center of mass of now these 2 point masses will be, we can figure out like as a function of d. So the center of mass should be shifted more towards 8m and away from 4m, because this is a higher mass. So what will be, let's say if I assume this as the origin, how far from here is the center of mass? So let's just assume this coordinate as the x coordinate now. So x cm will be, so 4m times 0, which is 0, plus 8m times d divided by 8 plus 4, 12m. So it will be 8 by 12, so 4 2s are 8, 4 3s are 12, so 2d by 3. So from here, the point of center of mass will be at distance 2d by 3. So obviously from here it is d by 3. Okay. So visually also sometimes you can figure out the center of mass. So the idea here is center of mass is as if for any system of distributed masses, the sum total of all the masses are sitting at the center of mass. So that is how you look at these problems. Okay. Let's suppose we have two masses, m1 and m2, okay, and they are separated by a distance r. Okay. Find the center of mass of this two body system. So it will be somewhere between m1 and m2 on the line joining m1 and m2. So if I take the origin as m1, then r center of mass, which is, let's say, from here to here, okay, is, so this we are taking as origin, so m1 times 0 plus m2 times r divided by m1 plus m2, or we can write this simply as m2r divided by m1 plus m2. So if we are looking at the center of mass from m1, then it is m2r by m1 plus m2. So if I say this as r1, which is the distance of the center of mass, this is the center of mass from m1, and let's say we say r2 is the distance of the center of mass from m2, then we can simply write r1 is m2r by m1 plus m2, and r2 is m1r divided by m1 plus m2. Okay, simple enough. Now if I divide this equation by this equation, so that becomes r1 by r2 is m2 by m1, or we can write m1 r1 is equal to m2 r2. So m1 times r1 equals to m2 times r2. Okay. Okay. So we found something interesting here. Let's start with this. m1 r1 is equal to m2 r2. Okay. Now if I differentiate both sides, which means what? Let's say I move m1 by a small distance r1, which will say dr1, then m2 will have to move by a small distance dr2 so that their center of masses remain the same. Okay. Let me say that one more time. So let's say m1 and m2 are here and their center of mass is here. This distance is r1 and this distance is r2. If m1 is moved, let us say by a distance dr1 outside. To keep the center of mass at the same place, m2 has to move the opposite way by a distance dr2. Okay. Or we can also write this as m1 change in position of m1 is this is equal to change in position of m2. What is this condition? This condition is to keep the center of mass of m1 and m2 at the same point. Unchanged. Okay. Now let us look at a problem around this. Let us suppose we have a 2 kg mass and we have a 3 kg mass. Okay. They have some center of mass somewhere. The 3 kg mass is moved to the right by 2 meters. How much the 2 kg mass needs to move to keep the center of mass unchanged? Okay. Good question. So let us say the 2 kg mass needs to be moved this side by x distance. Okay. So we can use this m1 delta r1 is equal to m2 delta r2. Okay. So m1 is 2 kg, delta r1 is x, m2 is 3 kg, and it is said it is moved by 2 meter. So x should be moved. So x should be 3 meters. So 2 kg is being moved 3 meters to the left to keep the center of mass unchanged. Okay. Now you might question on the signage. Remember, we took r1 in this direction as positive and r2 in that direction as positive. So we don't necessarily need to put a minus x here. It is like based on the convention, this is right. Okay. Now there is another way to explain why this formula holds true when the center of mass is unchanged. Let us look at that. So I give you a general formula when we have two masses m1 and m2, okay, separated by a distance whatever r. If m2 is moved by a certain amount, how much m1 needs to be moved to keep the center of mass at the same location? But let us figure out how we actually arrived at that identity. Let us say our coordinate system is here. So m1 is at a distance x1 from the origin and m2 is at a distance x2 from the origin. Okay. Then the position of the center of mass will be what? m1 x1 plus m2 x2 divided by m1 plus m2. Okay. Now if I find a small change in the center of mass, it will be brought about by small changes in x1 and x2. So m1 delta x1 plus m2 delta x2 divided by m1 plus m2. So if m1 is moved by delta x1, m2 is moved by delta x2, whichever direction it may be positive or negative, then based on this formula the center of mass will move accordingly. Now, if I want to keep the center of mass unchanged, which means delta xcm is 0, from here we get m1 delta x1 plus m2 delta x2 is 0. Okay. Now, then if you remember, if I reduce this problem to what we were looking at before, where we had m1 and m2, and we said, and let us say the center of mass was somewhere here, if the distance of the center of mass from m1 is r1 and the distance of the center of mass from m2 is r2, so both are in opposite directions. So, therefore, if I look at here m1 delta x1, so let us say there is a small change delta r1 that side. So, delta r1 plus m2 delta x2, let us say there is a small change in this side. So, this will be negative minus delta r2 is 0. So, therefore, m1 delta r1 we figured would be m2 delta r2. So, it is a matter of convention, but if you ask me, I prefer this convention over this. So, that way all the changes are in the same direction. So, the signage takes care of it itself. Okay. Okay. So, let us stick to this convention that a small change in center of mass is equal to m1, a small change in position of m1 plus m2 times a small change in position of m2 divided by m1 plus m2. Okay. Now, let us look at another problem. Let us say we have a 6 kg mass and we have a 2 kg mass. 6 kg is moved to the right by 2 meters. How much the 2 kg needs to be moved to move the center of mass by 1 meter to the right? Okay. So, 6 kg moves 2 meter, the center of mass was somewhere here. We need to find out how much 2 kg needs to be moved. I do not know which way, this way or that way. When we put the thing in the equation, it will give us that. But the center of mass, we need to move that to the right by 1 meter. Okay. Okay. So, we can apply this formula then. Delta xcm is m1 delta x1 plus m2 delta x2 divided by m1 plus m2. Now, delta xcm is 1 meter, okay, to the right. So, we will take everything to the right as positive. m1, let us say 6 kg is m1, it has moved by 2 meter to the right. Okay. m2 is 2 kg, we do not know how much it needs to be moved, that is what we will find out, delta x2 divided by 6 plus 2. Okay. So, 8 is equal to 12 plus 2 delta x2, or delta x2 is 8 minus 12 by 2. So, minus 4 by 2 or minus 2 meter is the answer. So, 2 kg needs to be moved this way by 2 meter, so that the center of mass moves by 1 meter to the right. Okay. Okay. So far we have done center of mass of a distributed system, but let's see how we can find center of mass of a continuous body. Okay. So in general, RCM of a continuous body, we will do integral over the entire mass of the body. So it will be 1 by total mass of the body integral R dm. Okay. So we take a small mass dm, which is situated at a distance r from the origin, and we integrate over the entire body of the mass. So, and divided by the total mass of the body, we get the location of the center of mass. Let's do an example and it will become clear. Let's say we have a semicircular wire, okay, of mass m, and let's suppose this radius is r. Okay. Question is, let's find out the center of mass of this wire. So how do we do it? Let's suppose at an angle theta, we take a small mass which is defined by d theta. So this part will be of length r d theta. Now what is the mass per unit length of this wire? Total mass is m. The full circumference would have been 2 pi r, but this is only half the circumference, so pi r. So we can think of this as the linear density. So r d theta length would have this times pi m by, so this times m by pi r. So this will be the small mass dm. Okay. Okay. So dm we can actually write dm as r gets cancelled, m by pi d theta. Okay. Now, how to find the center of mass? Now, just by symmetry we can see that the center of mass will lie on the y-axis. So xcm should be 0. We are only required to find the y coordinate of the center of mass. So ycm, how we will find that is 1 by m integral of the small mass that we considered, dm mass. The y coordinate of that dm mass will be what? R sine theta. This is r, radius r. This is r sine theta. Right? So r sine theta into dm. Okay. So 1 by m integral. Now dm we can replace with r sine theta m by pi d theta. And what is the range of theta? From 0 degree all the way to pi. So 0 to pi. Now we can take out the constants. So m and m gets cancelled. So r by pi. Sin theta's integral is minus cos theta. Okay. And the range is from 0 to pi. So this turns out to be r by pi minus cos pi is minus 1 plus minus minus plus cos 0 is 1. Okay. So this becomes 2r by pi. So the center of mass will be 2r by pi above. Okay. Okay. So far we defined what is the center of mass, and then we calculated center of mass of distributed systems. Then we did an example of a center of mass for a continuous body. We also did a few examples on change of center of mass when one or more bodies are moved in a distributed system. I will end this episode right here, and in part 2 we will start with a very important concept, which is motion of center of mass. So see you in the next episode.